Hi everyone, welcome to our first Moldflow, Simulation Moldflow Hangout. You have myself, Caitlin Shaffett, and Jeff Higgins presenting this information to you today. Next slide, Jeff.
Sure. Give me 1 second. That's interesting.
Sorry about that, everyone. So, anyways, I'm sure many of you are asking what a Hangout is. This originally started out as a pilot for SimCFD, but now Sim Moldflow and Sim Mechanical are going to be doing these Hangouts too. Really, it's just a very informal process. We're going to just kind of hang out, if you will. We'll walk through demos, presentations, and really this is for the customers. We can get feedback from you guys, what you guys want to see, what you have questions about, and just hang out about once a month and go over those issues that are actually happening in real-world situations. Typically, the Hangout is a 30-minute presentation demo format with 30 minutes QA. For today's Hangout, myself and Jeff are going to approach it a little bit differently. Jeff is going to demo the software, and I'm going to act as the voice of the customer. So I will be interjecting some questions that I feel that customers would have whenever using the DOE. So with that, I'm going to go ahead and give this off to Jeff, and we'll begin.
Caitlin, and it's actually great working with you today because I know we've talked a lot about the DOEs in the past, and I know we've had a lot of questions come up over time about what these DOEs are. So one of the things that I think is kind of interesting for us is to be able to talk to how we found the benefit of this and what our goals are for the DOE as we move forward with our customers. So my name, by the way, is Jeff Higgins. I'm a technical specialist with Autodesk. Caitlin, you're part of one of our expert support people, as I recall. Is that right?
Yes, that's correct. And thank you.
You are one of the voices that all of our customers get to hear when they call in and ask for assistance. So, it's great to work with you. It's great to have that type of conversation going today. As part of this, our aim for the DOE is to be able to look at some of the theory behind it. And I think when we talk about DOEs, many of us have a concept of what that DOE is and what they do. We've probably even seen real DOEs happen in real life, and we know how roughly time-consuming those can be. We need to get a better understanding of why we do it and a little bit of an overview as to what happens in this process as we set up this DOE. So us as a function of the process to set this up. So let's start with a definition. I don't know about you guys, but I have this tendency to kind of like understand this and what its background is. Basically a systematic approach to evaluating relationships between input factors and the output quality of a part. The benefit of this is we actually get the ability now to obtain higher quality data and more information about what our influences are in a DOE. The big difference between doing this inside of Moldflow and, say, doing this in reality are some of the capabilities that we have. For example, if we're looking at real simulation capability versus real molding trial capability, one of the big advantages that we have with simulation is, one, I don't have to wait for the machines to basically come up to temperature or wait for the variables to change. In my analysis package, it will happen instantaneously. The other is I have to take up machine time and lost production and wait for scrap material in order to get this to happen either. It's a very way of finding inputs to the overall process and what variables I can then use to create change or to create better parts.
So Jeff.
Yes.
Does doing the DOE in simulation eliminate having to do it in reality then?
In many cases it does. If you think about what the point of a DOE is, it's typically to find what those input variables are and what their influence is in on the part. So if you do this in a simulation package, you can find that same data without wasting the time on the injection molding machine. I take it today, Kate, that you've seen a lot of folks doing this on real injection molding machines?
Yeah, I was one of those myself in college, having to run through the DOE. It's extremely time-consuming.
Wasn't very fun, was it?
Nope, not at all. It was, like I said, time-consuming, and being at the press all day wasn't fun.
So let's see if we can add a little bit of fun back into this. One of the big things about the DOE is it will launch a series of analyses, whether it be a filling and packing or a fill, pack, and work. We can use the DOE builder that exists inside the software and specify variables that we want to use. So what things can we vary on the press? So treat it just like reality as they start setting things up. Which of these variables can I kind of tinker with in order to see what the change is? And one of the great things about this is if you look right here, even on this slide, you can see what the influence variables are and what % contribution they have. So what we're basically saying, and building right into the question that Caitlin asked, is can I do this in simulation instead of reality? The answer is yes. And I don't have to sit there and go through the math, and I don't have to do the weightings and all the manual measurements to figure out what this is. The software literally does it all for me. In fact, we're going to see that today when we take a look inside the software. So what types of DOE methods do we have built into Moldflow today? Well, when you use the DOE builder, you're going to see a series of options that pop up. One of the new ones that we just added is this parametric format. It was actually just recently added in our 2015 version of software, but we're going to focus on some of our more traditional capabilities, which is the single variable, the Taguchi, the factorial, or the Taguchi then factorial. And the reason I bring these up is because they all have different implications of what we're trying to do. The single variable is exactly what it sounds like. It gives us the ability to deal with one single variable that we want to worry about changing in the process, and we can see the influence of that variable on the process. Taguchi gives us the ability then to identify what the most significant variable inputs are. It's basically a mechanism for screening the variations that happen inside of a given process and then giving ranking to it. A factorial is significantly more complex, where we actually take all the variables that we want to use and we manually change them all, and then we get the ability to kind of tinker with them all and see what the ability to change is. My favorite, however, and the one we're actually going to look at today, is the Taguchi then factorial, because it gives us the ability to see the influences of all of these different types of DOEs that Moldflow can run. It gives us the ability to see what the influence of, say, a single variable in the process. It lets us see what the variable influence is from Taguchi, and then it allows us to use that Taguchi ranking in order to use the factorial type information and change the highest ranked variables in the process to see what our influence of change was. When running these different types of experiments, there are often obviously ways to set these up. Depending on the number of variables that you use, you'll get a different number of runs of experiments. And you can actually see that today when we start changing the number of variables that we're using. This is a great way of starting to build this information out. The disadvantage of the Taguchi format, for example, is it cannot detect complex interactions between the input variables. That's actually where the factorial starts to become significantly more powerful, is it's very comprehensive. It gives us the ability to see what all of those interactions can be. The disadvantage to the factorial, though, is if I run all of these variations of these variables independently, I get tons and tons of simulation runs. You can actually see that here. If I have just a single variable, I have immediately 3 runs. If I go from 3 to 2 variables, I go from 3 to 9 runs. The number of runs that build based on this complex interaction gets quite extensive. Using the Taguchi then factorial, which ironically is our default, it runs the Taguchi, finds that ranking information that Taguchi is so famous for, and then gives us the ability to run whatever those top ranked factors are. Now I can change this number to be whatever I want. If I'm only interested in whatever the top influence factor is, then right inside the software I could just use 1. The default is 3. I've been known to bump it up to 4 or 5, depending on how many of the variables I'm using inside of the Taguchi analysis to start with. So let's take a look at how this is all done inside of the Moldflow software today. So this is actually something that's kind of fun to get into, and we're actually going to take a look right at the Moldflow software. In fact, we've got this little sample part, and in this part you can see a couple of interesting things right up front. One of the neat things that you can see right in the very beginning of this is you can see that there's a couple of different colors. And since Caitlin is acting as my voice to the customer today, Mr. Customer, can you see these different colors on the screen here?
Hello, Jeff. Yes, I can. Looks like a green and then a lighter green.
There you go. Yeah, so we've actually got a couple of different colors. In fact, at some point, I maybe ought to change these colors and make them more pronounced, which is very easy to do inside the software. But basically what we've done is we've put these ribs onto a separate layer on this little RC car chassis, and then we put the main wall of the chassis onto a separate layer. Now that's going to become important in a minute when we start looking at the DOE setup, but I wanted to call that out in the very beginning here just because it gives us a lot of capability now of seeing kind of what those interactions are. In order to set up my DOE, it's pretty simple. I don't change my standard workflow at all inside of Moldflow, so if I'm going to do a fill, pack, and warp analysis, I basically use that same setup. And I can do the same thing, whether it's a cool fill, pack, warp, it's a cool FEM fill, pack, warp, if I'm doing any of the complex interactions type analyses, that part of this doesn't change. So the initial setup of this as a function of the DOE is exactly the same as everything you would have done up to this point. So use your traditional type of setup in order to get this started. The great part about this is whatever your processing conditions are now become your starting point for your DOE. It becomes your center point. So it gives you that ability to start testing that processing window and then start varying around it. So this is a great way of defining what that process is. And then to set up the DOE, it's literally this easy. You'll notice that right underneath the Process Settings tab is this DOE optimization option. In order to set this up, I simply double-click on this, and you'll notice that the DOE Builder is going to appear for me. Right? And the DOE Builder actually shows all four types of the DOEs that we just talked about. It has the single variable, it has the variable response, which is Taguchi, it has the variable response surfaces, which is, of course, the factorial, and then we have the variable influence and the variable response, which is the Taguchi then factorial. The reason why I keep using the Taguchi and factorial names is because those are the traditional names that we would be familiar with inside of the injection molding world. That's what we use quite a bit when we run DOEs. So Caitlin, when you were running DOEs out on the shop floor, what type of DOE did you run the most? Do you remember?
I think we use factorial most commonly.
Yeah, actually, that's probably the most common to use in injection molding because it is the variable response, right? It's the ability to change a single variable and kind of go through that. And as the process of that, that's exactly probably the reason why you were telling me earlier that it was very time-consuming, in some cases probably even difficult to complete, right?
Exactly. Jeff, let me ask you this question real quick. Do you see, what do you see in the field when you're out? What method users commonly use?
I was kind of a student of Taguchi when I was doing it myself, when I was a process engineer at a company in Pennsylvania. I liked the ranking system that Taguchi used, but we were a little odd. You know, when you're out in actual manufacturing, I would have to say probably 80% of the times I'm seeing factorial.
Okay.
Yeah, and that's not a bad thing, right? I mean, it's a good way of getting those response influences on the overall process. So a couple of things to take note of here in the DOE Builder is, selecting your type of DOE. Of course, if you did want to do every single one of those runs, you can actually see what the change is to the overall response. Now, something very interesting is happening. You notice when I change from one type of DOE to another, the number of runs down here at the bottom changes. Now, what this is basically showing me is the number of fill, pack, and warps or fill and packs or however many runs it's actually going to have to make in order to represent this in reality. So a DOE is doing literally what you would have done on the injection molding machine. It's literally changing the variables and then running more analyses so that you can actually see what the influences are. Now, remember before we said that the variable response and the variable influence together would probably yield the least number of runs. You notice here that I get 15, but if I go to that one, I'm actually getting 19 right now. And I'm going to show you why. Right now, if you look at my variable influence then response, I've got my number of variables set to 3. If you look, the total number of variables that I've set up on the next page is literally 3. So I'm not actually saving anything right now by going to this. But if I were to change this number to, say, 2 and just use the top responses, the top 2, notice that number has gone down. So even though I'm running 2 DOEs, this number goes down. On the flip side of that, too, if I left that number at 3 and I selected more influences, right, you can see that my number of runs has gone up significantly. But to do that same thing in a factorial run would have been 43 runs versus the 23 I can get by picking the top ranked ones. So there are some significant advantages in here of picking specific variables that you want to use and then ranking them and probably using the top ranked ones. The second page is exactly what we were talking about, being able to pick the input variables that we want to vary in the process. And you can see we've got the mean value, the min and the max values that you want to use. So you can see what the variations are within the ranges that you're going to specify. Now, all of the inputs are one step to this, but of course the quality outputs are the next step. Now, by default, everything is selected, so all of the outputs are selected. So everything from volumetric strength and bulk temperature to even my warp deflections are all selected here. And then there's a ranking system that you can apply to these as well. In the ranking system, I can go from 0 to 10, 0 meaning that it has no weighting in the global weight, which we'll talk about shortly, and 10 meaning it is the heaviest weight. By default, everything is set to 1, so it's given all equal weighting. And most of the time when I run a DOE, I'll run these all set at 1, so they all have equal setups.
Hey, Jeff.
Yes, Caitlin.
When and what type of instances would you want to weight them heavier versus just 1?
A lot of times when I have customers dealing with, say, warpage as a critical fit to some type of component, living in the Detroit area, I deal a lot with automotive companies. And, bumper fascias or dash components and all that have to have fit and function and appearance characteristics to go with it. So for those guys, a lot of times the deflections are much more important, so they'll weight those heavier than they would, say, just the base filling criteria. Or as part of that, they may be more interested in the material shrink, so they might weight that heavier. On the flip side to that, I had a company just recently that was trying to manufacture a component that had a series of holes in it, and they were trying to control the location of a weld line. In their particular case, the filling criteria was much more important than it was to anything else. So they were looking at the ability to fill, the total part weight. Those were the ones they weighted heavier, and they kind of ignored warpage. So you'll weight these heavier all based on the criteria of your part, so that as you're defining and simulating your part, the goals are given the most appropriate weighting.
All right, that makes perfect sense, actually.
Great. The last step to this, of course, is being able to set up here so that we can see if there are any problems in the process, what we can do about it. Now, the option that we have here for relaunch is kind of an important one, because we can set this to relaunch up to 20 times. Now, the reason I say this is important is because as we start varying the variables in the process, one of the things that becomes important is the fact that we can actually make the part. I've seen a couple of times in the DOE where we maybe vary the melt temperature, the mold temperature, or the injection speed, and it will yield a short shot. Well, inside of our DOE software, that's unacceptable. But rather than just saying, hey, this creates a short shot and it's totally unacceptable, we try to redefine that window, basically constrain it a little bit tighter, and see if there are some variables in there in order to actually test the variation that we've got while still producing a good part. I recently had this happen also with another company where we were going through the process of running a DOE, but by changing the melt and the mold temperature to a temperature that was too cold, it yielded a short shot. That's a real problem. It actually took about 10 iterations inside of the DOE, meaning that it would detect the short shot, redefine the criteria, and rerun it in order for it to come up with that. So we actually set the number to 20, found out what our processing window was, which was really, really cool, and then we were able to find out what our sensitivity was within the available process on that part. So the DOE has a lot of built-in intelligence that a lot of people tend to ignore. So as part of the DOE, though, the setup is only one given part of it. And one of the things that I want to call out as a critical component to this is the fact that when we're looking at the DOE, we come down and you'll notice the exact same results right inside the software that you would have had before from any type of a Moldflow analysis. So remember, we set up those set points in the very beginning. those set points are our starting points. And as part of those set points, you can actually see here, we've got our filling animations. We can still see our pressures through time. We've got our orientations. This is a fiber-filled material, right? So we still have our orientations that we can see inside of the part. We can see how the fibers are going to orient. We can even check the tensor of orientation. So all of those same base types of analytical outputs that are very, very familiar to us in Moldflow are all still here on that base analysis. In fact, if I even scroll down a little bit further, you can still see that we've got our warp capabilities. We can see what our deflections are. And all of these are the exact same functions that you would have done before. So we're not changing the process that you've got, and we're not even limiting the information that you have, because I still have on that base analysis the same capability to see my deflections, to see what my part is going to look like, and to get into those advanced types of animations, to be able to see what's happening throughout the cycle. So I can see my temperature or my pressure variations, make sure that my cavities are pressurizing properly, and where the part is freezing. So all of this is critical information to making decisions about the part. Where the DOE becomes extremely powerful is the next step to this. Because you're going to notice that we have a whole new folder of information that exists down here below what is now our deflection outputs. And if we take a look at these, you're going to notice there are a series of them in here that are XY plots. You're going to see a bunch of surface plots. And then you're going to see some down here at the bottom that are just regular types of plots. And we're going to dig into each one of these and start to get a feel for what these mean to me as a function of this process. So if we take a look at, say, our bulk temperature, one of the pieces to this that is extremely critical is that I can see what the influence of my temperature now is, or my bulk temperature, by varying something like this dimensional factor. Now remember, when we looked at that layer structure in the beginning, we saw that the main wall was on one layer and the rib structure was on a separate layer. And that's this dimensional factor we actually set up in our DOE. In fact, I'll show you that here in a second. We set up in the DOE as one of our input variables a geometric factor for ribs, meaning that we can now vary that rib thickness by plus 5% or minus 5% or anywhere in between those. So we can start to see what that means. And if you notice, by changing the thickness of those ribs, I can see what the impact or the impact of change is now on the temperature of the bulk temperature of my part at the end of fill. By going back to this, I can actually right-click on it and show the properties to it, where I can now see things like my melt temperature having an influence, or my injection speed's influence on the temperatures that I've got. So one of the things that's really, really powerful about the DOE is literally the fact that as I go through the DOE, not only can I set up what my X and Y variables are, but I can also then change these other variables to see what the influence is. Now, in this particular case, I might not care so much about the dimensional factor as I do say about the melt temperature as a controlling factor. So maybe in this case, I take the dimensional factor right here to 0, which means it's at its main position. I see what the influence of melt temperature is now on my bulk temperature at the end of fill. And then I can change things like my injection speed to see what the influence is on this process. And I can see now at different melt temperatures what that variation is in my bulk temperature. The XY plot is only one of the plots that we can get into. We can also start to get into some of these surface response plots. And this is where this also starts to add a lot of information. And you'll notice that this plot in particular is a three-dimensional chart. This chart gives me an X, a Y, and a Z axis that I can now see on the screen. And it defines to me what I'm looking at. So for example, the X-axis is listed here as melt temperature. The Y-axis is my dimensional factor, and the Z now is my injection pressure. So I can see at different points on this surface plot, I can even query on different locations of the surface plot to find out at different points or different set points of of melt temperature and injection speed, what the overall response to my pressure is going to be. And I can actually start to use this response surface to figure out what my influences are on the part. That's extremely critical. And again, just like everything else, when we start to look at the DOE, things like my injection speed are going to be just as critical. And you notice as I change my injection speed, you can see what the influence is on my injection pressure. One of the things that makes this so critical to the DOE, though, is to be able to see what those responses are. For example, I do this quite a bit when I'm looking at the response surfaces, is I'll go into a z-axis view or a y-axis view, because it gives me the ability now to see what type of a spread from side to side I have. Because this shows me that no one single variable in any direction here is giving me just a linear impact, right? I can see that this all has a little bit of width or thickness. Probably the smallest amount of impact right now is this axis that we're looking at here, right? This is this y-axis that we're looking at. So my dimensional factor is probably the least amount of influence, but it's still having an influence on this product. As an analyst, I love looking at the surface responses, whether it's for sink marks or wall shear stress or pressure like we're looking at now. This gives me a feel for which of these variables is going to have the biggest impact of change. In fact, I can even verify this by looking through the log system inside of my software. And you'll notice that one of the key pieces to this is as it runs through, say, the Taguchi, you notice that it's actually giving me a % ranking of the input variable on the output that we're looking at. So for wall shear stress right now, you'll notice that the biggest influence on wall shear stress is melt temperature. That's really interesting. So if my part is very highly stressed and I'm worried about it, say, cracking, I know that my melt temperature now is the variable that I need to play with in order for that to change. And I can keep going down through this, even things like my warpage get ranked, so that I can find out what my influence factors are for warpage in any direction. And now this is where the weighting comes into play, because we take a global weighting of this based on those weighting factors that we were looking at, and then we start to apply that to the total. So right now, my dimensional factor is about 38% influence on the part. My melt temperature is about a 38% influence globally on the part, and my injection speed is about 22. Now that doesn't mean that on specific variables these numbers wouldn't be higher, but as a global weighting it gives me a really good feel for what my influence responses are. And again, if I come back here, I can actually look at those and I can see what those responses are right here on the surface. So let's take this one more step. Right? As an analyst, all of these surface responses for things like deflection and temperature and the three-dimensional charts, all very, very powerful ways of seeing influence and being able to control the variable to see what the change is extremely critical as well. But trying to communicate that out to somebody in a three-dimensional chart is sometimes a little challenging. So one of the things that you can do with the DOE when you're trying to explain this to somebody else, you start to show it to them in a mechanism that makes sense to them. For example, on this particular part, there's a couple of really interesting things that take place. Now, I can show this result, for example, as a standard type of plot, just a standard shaded plot, where I can see the part and I can see the filling pattern, right? But any of us that have dealt with the software for a little while like to use that image that we just saw on the screen a second ago, which is that contour view. So if I go back to this contour view of the part, you can actually see, based on these contours, assuming that all of these contours are written at equal time intervals, I can see if they get closer together. I've got a little bit of hesitation. They get further apart. I'm starting to racetrack, or the material is speeding up. So you can see here towards the end, the material is moving very, very fast. I've got these little cutouts in my part. I can see now that in these cutouts how much hesitation I'm getting, how much faster it's moving down the rib structure. All of this is critical information to have. But remember, the power of the DOE is literally being able to see the influence of change. One of the big things that a lot of companies like to talk about, especially when they've got variations in wall thickness, is what happens if I change the structure of my part? What happens if I change that rib structure? You notice that as I make that rib structure thicker, right, I can see these lines here start to accelerate. As I start to slow this down, you can see that the rib structure starts to slow down even more. The lines are moving back. That tells me very quickly that the rib structure being smaller is starting to equalize the speed at which the material is moving through the rest of the part. So I can either make these ribs really thick and get a lot of race tracking down them, or I can come down here and make them really thin, and I can see what the hesitation is. On the same token to that, I can see what the influence is now of injection speed, right? How is the material freezing, causing different levels of hesitation? In this case, you'll see that the faster I move it, the less time I have for this to skin up, the less hesitation that I'm getting in the part. So for somebody who needs to be, or needs a visual description of this, using the actual graphical outputs and the variable responses here gives me the ability to explain to somebody using a very clear mechanism what the influence is. The cool part about this is if I'm trying to control things like weld line placement with thickness variations, just like we're doing here with the ribs, I can see how these contours are going to move around, where my resulting weld lines are going to be, what I'm doing with the part. Really ingenious ways of starting to come up with some resolution or some variation that might need to take place. And this holds true across the board for all the different types of outputs, whether I'm concerned about temperature variation of the part, temperature at the end of filling, how the part is freezing, all of those things are here. But the thing to keep in mind here also isn't just the fact that we can see these variations, but let's get back to this warpage output that we were looking at just a little bit ago. On the standard analysis, we could see the shape of this part. Many companies get really concerned about the shape of the part or the warpage that you're looking at. And just like we saw before, I've magnified this warpage output by 10 times. So you can see here that is a 10 times magnification. If I were to say set this back to a single magnification, it's about what your warpage looks like. We're going to set this back to 10 just so we can use it. But the neat part here is, watch what happens when I start to change my melt temperature. I can actually see what the response is to my melt temperature on the ability to control warpage. And you can see that it's not a big response. Remember, when we were looking at those variable responses, we could see in the log file that the dimensional factor had the most influence. In fact, if I go from end to end here, you can see exactly how much influence I have on the shape of this part just by changing the dimensional factor. On top of that, changing the injection speed also is changing the warpage of the part. The great part about this is when we were dealing with this particular company, looking at the warpage variations that we've got, they said, what is the biggest influence on warpage? And we came back and said, it's the thickness of your ribs, because as we change the thickness of that component to this part, we can see what the influence is of warpage. But we also said these other components also play factors, but you cannot fix this in process. And the really interesting part about the DOE was, while we found the biggest influence, we also proved that they could not fix the part from where they were. They had to make some level of a geometric change. Many times when I've been out on the floor, I've heard people say, we're just going to process this out, or we're just going to change this. A lot of those cases aren't really going to work. Being able to validate that the change will or won't work, or how much variation I have, really shows the power of a DOE and really gives the simulation the ability to communicate a lot of change very quickly. So what we're basically trying to get to with the DOE capability is by adding in a couple of runs in the very beginning. And in fact, when you all took those poll questions, mentioned that, in fact, most of you mentioned that it takes about a day to run a DOE. Some of you said you didn't do it before. Some of you might have said it takes a little bit longer. There are all types of solutions that are out there today to make these DOEs effective for you and start providing you with answers very, very quickly.
All right, thanks, Jeff. That was awesome. You did a really good job. Almost like you've done that a time or two before.
Once or twice. It's one of my new pet projects.
Oh, is it? Well, we had at this time we're going to go ahead and open the floor up for questions. That said, we did get a question that came in. The customer would like to know information, or he's saying it would be very interesting to know how the dimensional factor was defined. I'm assuming in your study there.
And so when we looked at this part in particular, it was a dual domain model. So the thickness on the part was actually a property. And that's one of the big things that we have to focus on right now with the DOE is we can only change properties and inputs. We don't have the ability to do, say, a geometric change to parametrically to a model. So on this particular model, you notice when I was changing the thickness, it wasn't literally changing the thickness of the rib. It was changing the property definition of the rib. And we do it by setting up a percent change. So I can do a 50%, 20%, 10%. On this part, we were doing just a plus or minus 5% change to the rib. What we ended up finding is if we went on about 17.3% start creating short shots. So did a 5% change so we can see the influence, and that was simply by changing the property thickness definition on the model.
Okay. Another question that just came in, is it possible to change the size of the gate diameter as a variable?
As long as the gate diameter is placed, as long as the gate diameter is a beam element, the answer is yes. You can place the gate onto a layer just like you did with the rib structure here, and you can give it a percent change, which will change the diameter effectively of that piece.
Okay. Is it possible to set up a valve gating open-shut times as a variable?
I haven't tried setting up a valve gate timing yet as a variable. I'm sorry, Kate?
I was just going to say that's actually a really good question there.
Yeah. I'd actually have to do a little playing with that one. It does have a property table, but I would suspect more that we would be more inclined to find what an optimal point for opening was and be more focused on the primary process settings. But it's something we can do a little investigation on. In fact, with our new version of the parametric DOE, we might be able to do a little bit more with it.
Okay. Next we have, is it possible to show weld line visual defects?
We can show weld lines a couple of ways inside the software. So we've got the weld line output. Normally when I'm trying to show the weld line placement using the DOE, I'll use the contours. It's a little bit easier from the filling output to show somebody where the melt fronts are meeting and then show the shift in melt front by actually moving the contours around. As far as visual defects, there is the ability as the response surfaces to see sink marks and to see warpage, which are the primary visual defects that we focus on inside the software. So you can use those as surface response variables and output surfaces. So you do have the ability to kind of analyze those as well. The question I would end up coming back with is what other types of visual defects are you looking for, and what mechanism are you using to find them today in the software? More than likely, we can still use that mechanism and show the responses in the DOE, but we would end up needing to put a little definition around it.
Yeah. So I actually had a question for you. So one of the biggest concerns with the DOE, as we talked about when first starting this out, is time. It takes a long time to run it in reality, and it takes a while, a day or so, to run it on the computer, is what we've more commonly found. Is there any way that we can optimize this runtime, like the cloud, for instance?
The cloud is a great solution. In fact, we had a company in Florida a year and a half ago that was trying to run DOEs, and based on the hardware requirements that they had, it was actually taking them about a week to run the DOE. And that's just a hardware limitation. When you're running on your computer, you've only got processors and so many cores, you've got so many licenses. And there's all types of reasons I've heard in the past for people to not run DOEs. The big benefit of the cloud, and I'm not, and keep in mind, this is not an advertisement for anybody to switch to the cloud, but it is a significant option for anybody that's thinking about it, because the cloud as a definition or as a means that I now have access to unrestricted or unrestrained solving. I was going to call it infinite computing, but I think that's a bad definition. It's unrestrained because I have access to so many machines that when I launch a DOE, for example, and I do the Taguchi then factorial, it'll do what is 3 runs rather than having to focus on all of the independent runs. So if I launch the Taguchi then factorial, it will make the initial base run, which it will run on its own. It will then make a third set of runs where it will set up all of the Taguchi runs that have to take place and run them all simultaneously. And when those come back and the rankings are complete, it'll then run all of the factorials. So in basically the time span of 3 runs, I get all of this DOE data on the cloud. Now that's not to discount hardware that people have today. If you've got a machine that's got a lot of computing power, you can still run this on your local workstation. Just remember that it will queue up the jobs and run them accordingly. So depending on the amount of cores and processors you have, it may take a little bit longer, but it's still an option you have. I really, really like the cloud today, Caitlin, for running DOEs.
So another question that has come in is, does the DOE compatibility also work well with birefringence?
Yes, it will. The birefringence as an output would have to be set up, but yeah, you can still do the same type of thing with a model that's running birefringence, yes.
Alrighty. And when would you not want to use the both Taguchi then factorial?
I just had a case come up recently where we knew we wanted to see 3 variables and we only wanted to see these 3 variables. And because of that, the Taguchi ranking wasn't going to be that critical to it. So we basically bypassed the Taguchi and just went right to the factorial because we knew what 3 variables we wanted to look at. We knew we wanted to look at all 3 of them regardless of what the weighting was. So it all depends on what you're trying to do. If you're trying to communicate to somebody what the impact is of the variables, the Taguchi is a great mechanism. It has a lot of good outputs. The surface responses are great. If you want to show somebody just what the influence is on the model, the factorial is a great way to go. Personally, I use the Taguchi then factorial on most new studies for a very simple reason. I don't know which variables are going to be the highest ranked, and I don't know which are going to have the most influence. And because of that, if it only has a 1 or 2% influence on a part, I'm looking at 5 variables, it's probably not going to mean much to me as an output. So using the Taguchi then factorial reduces my number of runs and allows me to focus on the areas where I have the biggest influence. So it all depends on your objective to it. If you want the weightings, the Taguchi is the way to go. If you want, you want specific variables, the factorial is the way to go. If you don't know what you're after and you want to see what the biggest influence is, the Taguchi then factorial is really the way to go.
Okay. The next question I have is how long does the DOE run, for instance, with 3 runs take compared to a normal fill pack simulation? Does this mean 3 times the normal run time?
Yes, it does. The thing to keep in mind, though, is it all depends on how your computer system will handle it. In many cases, most computers will run things simultaneously. This is a series of actual runs that you would do on your computer, which is exactly what makes the DOE so powerful. But the other side to it too is that if you're doing, say, 3 runs, you're going to get a total of 4. You're going to get your base run, and then you're going to get your 3 variable runs. So you're going to get a total of 4 runs. But if your computer is typically running, say, 2 jobs at a time or 3 jobs at a time, then it will run significantly faster. The most I've seen probably on a local workstation is about 4 jobs at once. So if you're doing something significantly more complex, you can maybe run 4 jobs at one time. But if you're running, say, 24 runs, it means it's going to be roughly the time equivalent of 6. So if you're running it on the cloud, you probably get it done, depending on how you get it set up, you might get it done in the time of 2, or it might get it done in, so yeah, it is actually a series of actual simulation runs to get those response variables.
We just had another question come in. It's a pretty good one. Which industries are you seeing the most demand for this sort of DOE? You mentioned automotive in the presentation or the demo, but do you see it in medical applications very often?
I do. In fact, I just saw it in consumer products on on Wednesday. I was up visiting a company on Wednesday that makes basically 5-sided boxes. They make containers. And they were interested in it for sizing flow leaders. So the thickness variation we got into, they were actually doing that for flow leaders. Automotive is big for it right now. Aerospace is looking at it quite heavily. I see absolutely no reason why the medical industry wouldn't jump on this just like everybody else has. In fact, I would think for the medical industry especially, this would be considerably more critical because things like weld line placement and even stresses in the part as a response surface variable would be significantly more critical for medical than it would be for most other industries. So this would be a great way for the medical industry especially to start kind of diving into what their manufacturing process means to them.
Next we have, can we use just an injection location, or should the model be, should the gate be modeled as well?
That's up to you. The model we looked at today just had injection locations on it. In fact, the models I showed to the customer on Wednesday had the entire runner system in the tool model. We went clear to the extreme, and this is kind of fun, went clear to the extreme of varying the core and the cavity temperatures as independent variables. And we saw what offsetting the temperatures meant to the warpage of the part. So anything that you can basically set up as an input can become a variable for the DOE, and then you can start seeing what the responses are. So yeah, absolutely, you can do it either way.
Okay. Can this be modeled with 3D models too? I believe we just answered that.
Yes, this will work with any type of model that you have. 3D, so it works with 3D models with 3D runners, 3D models with beam runners, mid-planes, dual domains, beam elements. So any type of format basically that we can put in, it will work with. Now, some of our specialty capabilities do not have the ability to support this. Like our compression molding capability doesn't yet have the DOE built into it, but most of the standard types of injection molding have the optimization of the DOE function for it.
Okay. I apologize. I think we're going to jump back a little bit to the previous question. Can we make the same conclusion with injection location and gate? I'm not sure. You might not understand that.
I'm not completely sure, but I'm guessing they're asking if we could do a DOE with an injection location or with a modeled gate. And the answer to both of those is yes. You've got all the same functionality and variability on the gates that you would have on the main wall to the part and the runner system. So yeah, it doesn't matter if we have just injection locations or modeled runner systems or partially modeled runner systems. You can do the same thing.
Okay. We just had two come in that are sort of similar. Can the DOE be used with cool analysis, and can you do a DOE with an overmolding analysis?
I will answer the first one first, and I know the answer is yes. So with a cooling analysis, you absolutely can. And I think I just mentioned the project that I was working for the consumer products company earlier this week. We actually did do the cooling analysis as part of the variable influence. We changed the input temperature of the material, the coolant material, on the core side and the cavity side as input variables. So we could actually see what the variability was of changing both the core or the cavity temperature independently and see what the influence was on the part. I'm not 100% sure on the overmolding yet. I'd have to dive into it. Like I said, I know we don't have it available for all of the specialty capabilities that are in Moldflow, but I'd have to check.
I'm gonna chime in real quick. We do have the ability to use DOE with overmolding. Jay just let us know that.
Okay, good.
Yeah. So with that, I'm going to go ahead and wrap everything up. The data set for this will be posted on YouTube. There will be a survey that comes out, and users can what they liked, what they didn't like, if they have a suggestion for the next Hangout, and just kind of give us your feedback on what you thought of this Hangout today. Jeff, did you have anything else you wanted to add?
I just want to thank everybody for showing up today. I know we had a really good attendance, and we got some great questions out of it. I hope everybody goes back and runs the DOE now and finds it as informative as I have found it since I started playing with it a couple years ago. This is really a great way of starting to isolate effective variables in an analysis and starting to be able to communicate it out to other people for influence.
All right. Thanks, Jeff.
Thank you. I appreciate everybody's time.